Welcome to Homework Lib.
Hi, so for this problem, first of all, let's do a super small review about what is going to happen when we have an acid. Let's call it a general acid BH, which is a weak acid that is going to be in equilibrium with the conjugate base plus H plus. That is the hydrogen extra. Maybe you want to write this down as H3O plus, but that depends heavily on what professor you're dealing with or at what level you are working, but both of them work in this case. Remember that the concentration of hydrogen is the same as the concentration of H3O plus. So I'm going to stick with H plus just for simplicity of the explanation. Okay. So let's remember that if we start with a C0 concentration and we do our ice table, the change in this case, it is going to be minus x, so a portion x of BH is going to react, and we're going to have a change of plus x on both of the sides. That means that at equilibrium, we're going to have a quantity C0 minus x times x times x. Now let's recall the definition for the acidity constant, which is concentration of the conjugate base, concentration of H plus, divided by the concentration of our initial acid. Replacing these values, you may see directly that this is x times x, this is x squared, divided by C0 minus x. Okay? Now, in order to solve this problem, you have two different options. The full-on method, that is solving the quadratic equation. If we rearrange this, you're going to find that the associated quadratic equation becomes x squared plus Ka x minus C times the acidity constant. C0 times the acidity constant equals to 0. So that is the first option. Plug in your values and solve this quadratic equation, and the value for x will be equal to the concentration of H plus. Okay? The other way to solving it is in the case that C0 is much larger than the expectation that you have for the value for x, we can approximate that C0 minus x is close to C0. Okay? And in most of the cases, that is going to make sense. For example, here we have a C0 of 0.1 molar in all of the cases that we will deal with. That means that for C0, that means that, for example, in the case that we have a pH equals to, let's say, 4, that implies that the concentration of H plus is equal to 10 to the minus 4, which indeed it is going to be much smaller than the concentration that we have. Also, if we have a pH of 2, the value would be 10 to the minus 2. So in that scenario, then we would not be able to use that approximation, because if we have 0.1 minus 10 to the minus 2, the result would be the result would be 0.99. So we are starting to get closer into a region where the approximation is no longer valid. Okay, so you can use the some possible values for pH to know if the approximation will work out or not. In this case, since we're dealing with weak acids and we have a relatively high concentration that is equal to 10 to the minus 1, then we know that approximating C0 minus x to C0, it's always going to work in this case, just because the high concentration of the acid that we have. In the case that the concentration was in the range of 10 to the minus 4 or 10 to the minus 5, then you would need to do the full quadratic expression. Okay, so with that out of the way, I'm going to go ahead and we are going to find the possible values for x squared. If we do the approximation that we mentioned, these equations becomes x squared divided by c0. This implies that our value for x, it is going to be Ka times c0 and taking the square root. So now we can do these calculations for all the different acids that you're given. So I'm going to write down the Ka values and we are going to do the calculation for the value for x. And with that, we can do the calculation of the value for the pH. So here I'm going to list everything. So I'll just pause for a second. So these are all of the possible values that we're going to have for K for the different acids that you are required to do. So let's do the first one and then I'll give you the result for all of the other ones. Okay. So x is equal to the square root of Ka times C0. So for the first case, 1.1 times 10 to the minus 2 times 0.1. The result of x gives us, okay, so here is the procedure for solving the first one. In this case, we know that x is equal to KaC0, and we know that the x, it is going to be equal to the concentration of hydrogen. So replacing the value for Ka and my initial concentration, I find a value of 0.33. This implies that our pH, it is going to be minus the logarithm of that concentration minus the logarithm of x, and that gives us a value of 1.48. Now, this value is starting to get close to the approximation that we made in this step. So if we go ahead and solve the full quadratic expression, we find a value for x equals to 0.028, which corresponds to a pH of sorry, a value of 0.28, not 0.28. Of what? Sorry, just checking. This was 0.28 indeed. Yes. So the pH turns out to be 1.55. And also here, a small, this one's 0.033. So yeah, everything matches up. So with this procedure, what we can do, I'm going to erase these values. And we can get the results for each of the different acids. Okay. So for the first one, replacing the values, I'm going to write down just the value for x that we found, 0.033, and the pH, that was 1.48. You may realize that the difference in pH with this method and the quadratic equation, it doesn't change that much. And I will give you the values for all of the other acids following the same procedure. Okay. So I will pause for a second just to give you the final results. Okay. So the values for each of the different acids are going to be 6.78 times to 10 to the minus 3. And recall that this is in molar in all of the cases. Next up, we have 4.24 times 10 to the minus 3, again in molar. then 3.61 times 10 to the minus 3, again molar. And for the final one, 5.39 times 10 to the minus 5. And here it is times 10 to the minus 6, sorry. Okay, and the values for pH that we find with this is 2.17, 2.37, 5.44, and 4.27.